Okay, so we're here today to talk about pedigree charts and what they show us in terms of genetics. So a pedigree chart really is just a family tree that helps you to track a certain genetic trait. Most typically they're used to show inheritance of disease in families. That's their most realistic application. We do use them though to track simpler traits like, whether you have attached earlobes or free earlobes, just for practice. But typically they would be used for inheritance of disease. So I'm going to teach you today what it is, who uses it, and how to interpret a pedigree, because you're going to see them coming up as we move forward through the next part of the course, which is going to be talking about genetic disease, and then how do those mutations actually spawn from DNA and what DNA does, and get into more of like the molecular basis of it too. So when you're looking at a pedigree, that picture I just showed you, it's just a family tree. It's a chart of the history of the family over several generations. And there are actually jobs out there called genetic counselors who would most use a pedigree to help illustrate to a family what their risks are when they're tracking family history of a certain, usually a disease, in that family. So how do you read a pedigree? There's some really important things you got to make sure you're aware of in order to understand and figure out what a pedigree problem is trying to demonstrate. So first of all, you should realize that each kind of like row going across is a generation. So in this pedigree example, I have box 1 and box 2 are pointing to the first generation. We would call that generation 1. And then their children are stemming down from those top generation. So all of the people across this row would be generation 2. And if you stem down from there, generation 3, and some pedigrees go further and show more generations than that, but 3 is a good typical amount of generations to show. So basically everyone here in the bottom row are the grandchildren of the top 2 people. So the top 2 people had however many kids and however many grandkids. I'm gonna just real quick let someone else in. Here we go. Okay. So how do we read this? So you got to know what the symbols represent and what the coloring represents. And by the way, everything that I'm going to run through now, I'm running through quickly. I'm assuming you're not writing down notes really now. You are welcome to watch this and the recording once I post it and pause it as needed. And also my notes are posted on my website. So you're welcome to go and reference those. All right, so when you see a circle is going to mean that that is a female in the pedigree. A square is going to be a male. When you see coloring, that's going to mean that that person has a trait. When it's not colored, they don't have the trait. When you see a horizontal line connecting the female and the male, like this one here, box number 3 is pointing to it, that shows that that's a marriage, is a marriage line. And then when there's a line stemming down from that marriage, that's going to be a line indicating what box 4 shows, the children. Their children stems down from the marriage line. So if you follow that line, you're going to see that this couple, the generation 1 couple, has one daughter stemming down from their line, another daughter here, then they had a son, and then they had another son. So there are actually 4 children branching down from that first generation. And then some of those children have a partner, so you see more than 4 people in the second generation. But the line stemming down is how you know it was their child. And we do go in birth order. So this female child here that I'm circling, like with my mouse, this is their oldest daughter. And then you go to the right of that, this is their second oldest child. Then they didn't have a son until they had their 3rd child, and then their youngest child is another son. Okay, so you can read it from left to right in birth order. When we look at, I'm just going to kind of go back to what the boxes are showing us now. When we look at that as the birth order I was just talking about. So that's illustrated down here in the box on the bottom that I just reeled, number 5. So when we're looking at these siblings, you can see that the male is older than his 2 sisters. His 2 sisters are younger, left to right. If you see a colored in box or a colored in circle, that means whatever trait we're showing on this pedigree is there in that person. That person expresses the trait. They show the trait. So we color them in. If you see someone not colored, like over here or in all the other empty boxes, then that person does not express the trait of that pedigree. In this case, we are illustrating carriers of a trait, and they're not always going to be illustrated, but this picture is using it. So in this case, this person is not even a carrier of a trait. A carrier would be represented by a half colored in shape, like this one right over here. this person's a carrier of the trait. And remember, carriers are only possible in recessively inherited traits, because you can carry that recessive allele and not express it because you have a dominant one. And remember, for a recessive allele to be expressed, it has to have no dominant alleles dominating over it. You won't always see carriers illustrated in a pedigree. Sometimes the pedigree will only show you who fully expresses the trait, and then you'll have to determine who is a carrier. So just keep that in mind. This pedigree is showing a carrier, and you would be given a key if you were given a pedigree question. And if you don't see half colored in, that doesn't mean it's automatically dominant. It just means they might not be showing you carriers. So we got to know these symbols. When you construct a pedigree, you've got to know a male is a square, a female is a circle. An affected male who has the trait that you're tracking is colored. An affected female who has a trait that you're tracking is colored. So that's just how we distinguish those symbols. If you're showing carriers, and again, they don't always get shown, you color them halfway. If someone is deceased on the pedigree, we put a slash through them to indicate that they are deceased. So a male would have a slash through the square, female would have a slash through the circle. That means those people are deceased in the pedigree. If we didn't know the sex of the person on the pedigree, this is very often from, like, let's say a miscarriage of a pregnancy. If you don't necessarily know the sex of the person, and it's unspecified, again, typically because of a miscarriage, then we use a diamond shape. So it's not a square, it's not a circle, it's a diamond shape because it's unknown, sex unknown. A marriage line is going to connect the male and the female. And then if they're not married, but they did end up having kids, you'll see a dotted line connecting them, and then the kids branching down from that dotted line. Just little, deviation from the marriage line. If you see divorce, it's pretty much death of the marriage, which is indicated with the death slash going through the marriage line. That's divorce. And again, these are all on my notes on the website. Don't feel like you have to be writing any of these down. Okay, so that top word up there, consanguineous mating. That means incest. And yes, that happens in family pedigrees, and it actually increases the risk of mutations and disease to happen. So consanguineous mating, meaning like if two close cousins or even siblings reproduced, then you would draw two lines between them, not just the single marriage line. So when you see two lines connecting, that's consanguinity, that's incest. If a family has twins, we can indicate there's a difference between identical versus fraternal twins. And so we're going to draw them a little differently. So if you have identical twins, you could have identical twin daughters. So you'd have two circles, and they branch down from the parent with sort of like this diagonal type of line coming down from the parent, rather than a single line coming to each of them. So a diagonal line comes down from the parents, and then we connect the two daughters. This doesn't mean these daughters got married. I know it's weird, but since they are connected, we know they are identical twins. If these were fraternal twin sisters, we would not connect them with this line between the two circles. They would look like this. So remember, you can have identical twin girls or identical twin boys. You can't have identical twins that are different sexes, then they're not identical. So if you have fraternal twins, you have either a fraternal combination where there's a girl and a boy, and they could be reversed if the boy is older. You could have a fraternal combination where it's two boys, two squares, or a fraternal combination where it's two girls, so it's two circles. And again, the way we know it's twins is that it's like these diagonal lines, almost at the top of a triangle, coming down to those symbols from the parents, instead of a straight line that we would use for single birth children. So a sibling set, when they're not twins, you would see a straight line coming down from the parents, and each child would get their own branch down from that straight line. So these would be siblings where the boy is older. You could reverse that if the girl was older, put the circle on the left and the square on the right. Okay, adoption. You don't really see this in problems, and I'm not going to put out any examples where this is in the problems. But if you were interested in creating your own pedigree and you have adoption in your family, there is a distinction between adoption into the family versus adoption out of the family. So if your family adopted a daughter, this is how you would do it. So you would have the daughter as a circle, and you would have a straight line, but it's dashed, coming straight down from the parents who are her adoptive parents. So her adoptive parents would be up here, straight line coming down to the daughter, and you put a bracket around her. That is to illustrate adoption in. So the bracket is adoption, and then the dashed line is showing that she's coming into the family. Because if she was being adopted out of the family, it would look like this. So if she's being put up for adoption, you would have a straight line down because she was the biological birth daughter of those parents, but then you would put the brackets to show adoption, and then you would draw a dashed line out of the family, and you could connect her to her adoptive family and put the adoptive parents next to the biological parents. Right, so it's not typical to need that, to see that. Adoption's not as common, but it's come up in my classes before, so I figured I'd throw it in. So now when you're looking at a pedigree, the trickiest part, the symbols are easy. Once you practice them, you see them over and over again, you start to learn the symbols. But when you do pedigrees, you typically need to be able to think in opposite ways. You got to be able to think, is this showing me recessive inheritance, or is this showing me dominant inheritance? And then you got to also be able to figure out, or is it showing sex linkage? Those are the inheritance patterns we've talked about so far. We talked about autosomal recessive diseases, autosomal dominant diseases, sex-linked diseases, which are almost always recessive. And how would they show up differently in a pedigree? So that's what this is going to help us walk through. And again, all these notes are on my website. So just a quick reminder, those are the 4 inheritance patterns that we've done so far: autosomal recessive, autosomal dominant. Those are on the first 22 chromosomes we call autosomes. And then there's X-linked recessive and X-linked dominant. X-linked dominant is super rare. It's not many diseases work that way. Most X-linkage are recessive traits. So what I'm going to go through right now are clues, not rules. They're clues. They don't always hold true, but they're great clues at giving you a guidance of where to start in trying to figure out the inheritance pattern. So using these clues, when you think or you want to check for an inheritance and see if it's possibly autosomal recessive, these are the clues of what you would be looking for. And again, these are not rules. If the trait rarely shows up in the pedigree, so like in this picture, not many of them are colored in, that's a clue it might be autosomal recessive. Recessive traits tend to be rarer. That's not what defines recessive, but they do tend to be rarer. So it's not a rule, it's a clue. If you see it skipping generations, we can say, oh, maybe it's recessive because recessive alleles can be hidden or masked by a dominant allele. And some people could just be carriers and not actually show the trait. So that's another clue that it's recessive. If you see males and females pretty much equally affected, then you're going to lean more towards autosomal and not likely sex-linked, because sex-linked is going to have more impact on males, and we'll get to why in a little bit. And then one thing you should ask yourself anytime you start looking at a pedigree is, do I see anyone who's affected, meaning they're colored in, but they don't have any parents affected? If that's the case, you start with attempting it as a recessive trait. And you're going to plug in genotypes and see if that actually is a recessive trait using the genotype. So I use that question here, and I see that clue by looking at, oh, this daughter and this son both have the trait, but neither of their parents have it. That is my clue that this is a recessive trait. So how could these kids get it if their parents don't have it? Well, I know each of their parents must be a carrier for the trait. And again, remember, not all pedigrees show carriers, because then it's too easy for you to interpret as a student learning how to do pedigrees. So we could realize these 2 parents that my mouse is over right here, they are carriers, and what happened in the children who are colored in, they happen to inherit the recessive allele from each parent. So we would go ahead and plug in genotypes, which means assign the letters for these traits. And you would say, I think this is recessive, so that means anyone who has this trait is going to have 2 lowercase alleles, 2 lowercase letters. So I'm just going to use A's for autosomal. So I would give everyone who's colored in 2 lowercase letters, because I say this must be a recessive trait. So if it's recessive and you have it, you must have 2 lowercase letters. Then you're going to follow, where did they come from? Remember, every child inherits 1 allele from each parent. So you know this boy down here who's colored in has 2 lowercase a's. His parents must each have given him 1. So each of his parents are then going to be assigned a lowercase a, but you know they're not colored in, so they must also have the dominant allele that keeps them from having this trait. So each of his parents are going to have to be what we call heterozygous, or carriers of this recessive trait. Okay, so you could work your way up from there and start plugging in genotypes. You could also work your way down from this mother who has the recessive trait, but none of her children do. She has 3 kids without it. So you know these 3 kids must each inherit 1 of her lowercase a's, because that's all she has to give them. You got to get something from your mama, and mama only has 2 lowercase a's to give you. You're going to get 1 of them. but none of them are colored in, so they must all have a dominant allele to keep them from showing this recessive trait, and that dominant allele must have come from dad. So dad could possibly have two uppercase A's, or he could possibly have a lowercase a and just didn't pass it to them. It's possible. It's more likely he has two uppercase A's, but we don't know for sure, so we can leave that second allele for dad as a question mark or a little dash. You just don't know, can't be determined from this information. Okay, so then you can work your way through and find that information through the rest of the pedigree just by following the traits down, remembering every child inherits one allele from each parent. Just a reminder of some examples of diseases that can be inherited in that manner, autosomal recessive diseases. We covered Tay-Sachs, cystic fibrosis, PKU, sickle cell anemia. These are all autosomal recessive disorders. And that was from a little while back, but it still applies now if we want to see how these traits, how these diseases are illustrated in a family history. Switching gears now. Now, clues if you think you're looking at autosomal dominance. It's going to be just kind of like thinking opposite of what you were just considering. Clues are going to be now the trait is more common in the pedigree. And again, remember, these are rules. I'm sorry, these are clues, not rules. So if you see the trait is more common, it's in every generation of the pedigree, and the affected individuals all have a parent who's affected, it's in every generation, then this is more likely going to be a dominantly inherited pattern. So I would start with applying dominant inheritance principles. So that means everyone who's colored in is going to have at least one dominant allele. And that means everybody who's not colored in must have the recessive form of the trait. So I'm going to actually start assigning those lowercase letters to everyone not colored in. It's the opposite of what we did in the previous pedigree because we thought that one was recessive. So now everyone, I think, who shows the trait has a dominant trait. So everyone who doesn't show the trait must have the recessive form. So I am going to go ahead and assign everyone not colored the recessive two alleles. And again, I'm just using A for autosomal, the lowercase version for everyone not colored. Then from there, you can work through and figure out where those A's came from and go to. So if this son has two lowercase A's, he must have gotten one from the mother who had nothing but lowercase A's to give him. And he must have gotten the other one from the father. Because remember, you get one allele from each parent for every trait. So this father, even though he's colored in, he's got to have a lowercase a as well as the dominant A to provide to his son. So you can work your way through, and then down from the mother, this daughter has to have at least one lowercase a because the mother has only lowercase a's to give her. So you can work your way through up and down the generations and plug in who's going to then be heterozygous and have one dominant and one recessive, because they either got a recessive from their parent or they gave a recessive to their child. And so all of these dominant showing alleles are going to be accompanied by a recessive allele in there as well, based on the family tree, the family history. Okay, so these two boys down here are showing the trait, so they have a dominant allele, but they got that from their mother, and from their father, they must have gotten a recessive allele because he does not show the trait. Okay. And then since we see boys affected and girls affected evenly, we're also realizing this is probably still autosomal as opposed to sex-linked. Sex linkage is going to show up more in males for a reason we'll see in a second. So an example or some examples of autosomal dominant diseases that we did learn about previously. If you remember dwarfism, achondroplasia is a type of dwarfism, that's dominant. Polydactyly, having an extra finger or toes, that's dominant. And so is Huntington's disease, which is degeneration of the nervous system. Those are some examples of dominant, autosomal dominant inheritance patterns, which means you only need that one allele, faulty allele, to show the disease, show the trait. All right, switch gears again. Now we're going to look for sex-linked recessive inheritance on a pedigree. Now remember, the X chromosomes, sex chromosomes, they come in twos, right? You get either two X's like a female does, or an X and a Y. So the Y is super teeny tiny, and there's barely any DNA on the Y chromosome. Not a lot of linkage to the Y chromosome. So most sex-linked traits are on the X chromosome. Everyone has at least one X chromosome. Males have one, females have two. So most sex linkage is actually X linkage. It's on the X chromosome, just to clarify that. So what are some clues that we're looking at an X-linked recessive trait? If you see the trait rare in the pedigree, that's one clue that can lead you to thinking, oh, it might be recessive. If you see it skipping generations, it might be recessive. If you see fathers who have it, don't give it to their daughters, that could be a clue. I'm sorry, don't give it to their sons. That could be a clue because fathers give Ys to their sons and they give X's to their daughters. And then also, if you see more males affected, that's a big clue. Male, male, male. Only males are affected in this pedigree. So that's a big clue that we should try and attempt it being an X-linked trait and attempt to see if it's X-linked recessive. Because remember, males only have one X chromosome because they have an X and a Y as their combination. So if they have a faulty gene on their X, that's the only X he has. He doesn't have another X to have the dominant gene form show up. So the males have to express whatever's on their X because that's the only X that they have to use. Females have two X's. So if you have one faulty X and then one healthy X with the healthy allele, then you're good to go. You're going to just show the healthy allele. Okay, you're going to express that one. So the notation's a little different because when we use sex linkage, as you remember in the past, we're going to use X's and Y's and then like connotate if the trait is there on the X chromosome with a little mark or a slash of some kind on your X. So typing it out, it's going to look like this. So remember, use X and Y when we're doing sex linkage genotypes. So every male gets an X and a Y. Every female is going to get two X's. And now we have to determine where the affected X's are. Who's got a messed up X? So everyone colored in is going to have a messed up X. But they're boys, so they're going to have X with a little mark on it. That's my messed up X. I put an apostrophe with a Y. Then we've got to see where that messed up X came from. Remember, boys get a Y from their dad, and the X comes from mom. So moms are passing this affected X to sons. So the mom of this affected son must be a carrier of this X-linked disease. So mom has that affected X and one healthy X. So mom is fine. She shows whatever DNA is on her healthy X. She doesn't show her affected X because she shows her dominant alleles. This recessive one is hidden in her because she has two X's. The boy she passed it to has no other X to hide that faulty allele. So he has to show that faulty allele. That's the one that gets expressed. That's the trait that actually comes out. So you can follow it up from each of these affected males and realize their mothers must have been carriers for this X-linked trait, which means they have one healthy normal X and one affected X that has that recessive allele on it. Okay, and then this female, we don't know because she didn't have an affected son, so she's probably normal, but she could also have the recessive allele and just not have passed it to him. It's only a 50-50 chance. The mom could pass her affected one or her unaffected one. So that one's more of an unknown. So the carriers, the people we know for sure are carriers, are the ones who are mothers of sons who got the disease. So the mother doesn't have it, but her son does. Okay. X-linkage. Some examples of X-linked disease are color blindness. This is a fun colorblind test. I would not trust Zoom as being able to project the pixelation well enough, so don't use this projection to see if you are colorblind. But you would typically be able to see if there's numbers embedded in these spot plates here of different colors. Another example of X-linked recessive diseases are hemophilia. Hemophilia is a blood clotting disorder when you have difficulty clotting your blood. And another one is called ALD. It's a big, long word. It stands for adrenoleukodystrophy. And there's a great movie based on a true story of a child who had ALD and how his parents basically found a treatment for it that saved lives all around the world. Super great movie called Lorenzo's Oil. Maybe we'll get to watching that eventually. We'll see. Okay, so last type of inheritance pattern, and then we're done. There are 4. So we did autosomal recessive, autosomal dominant. We did X-linked recessive, so all that's left is X-linked dominant. This is super duper rare. There's almost no traits that are inherited in this type of pattern, but there are a couple, and there's one that's hairy face. I'll show you that in a second. What clues would we look for to see if it's X-linked dominant? If the trait is more common in the pedigree, that leads to thinking dominance. And if we see the trend from fathers passing it to all of their daughters, that's a clue. If all the daughters of a father who has it also have it, that's a clue. Like down here, number 7 has it and all his daughters also have it, that's a clue it might be on the X and therefore be dominant, because the X that he gives them, he only has one X to give them, and they are showing the trait, so it must be dominant because they're getting it with only having one affected X. Mom doesn't have an affected X. She's not showing the trait. So if you see males and females equally affected, then it could be sex-linked dominant, as opposed to if only males are more affected, then that's more likely X-linked recessive, because remember, males only have one X while females have two. So remember to use X's and Y's when you're doing the genotypes of X linkage. So again, we're going to put males having XY, females having XX, and then we've got to figure out who has affected X's. So if it's dominant, then the males who have the affected X are going to show it, and they have a Y. So they have one X and one Y. They have to have the affected X. Females are only going to need one affected X to show the trait. All the healthy males just have their normal XY, and a healthy female has her normal XX. Affected females who are colored have to have one affected X. They could have two affected X's, but then you'd have to see it coming from their parents on both ends, right? So this female has one affected X. She got her affected X here from her mom, and her healthy X from her dad, but it only takes one X to show up if it's a dominant trait. You only need one affected allele to show it up, make it show up if it's a dominant trait. So then we can plug in these two females down at the bottom, same condition. They have the trait, they must have gotten an affected X from one of their parents. The father is the one affected, so he's the one who gave them that affected X. So you really just got to be able to look up and down the generations and see where those alleles are coming from. So just remember, every child gets two alleles, one from each parent, and you work up and down. This is the one example of the X-linked dominant disease called hypertrichosis. It's also called werewolf syndrome. Oh, there we go. Hypertrichosis causes excessive growth of hair in places on the body that normally do not grow hair, like the face, the ears, and excessive growth, and all around the rest of the body as well. People can trim it, you can shave it, but it does keep growing back. But it's a very rare trait, very rare disease. It happens to be on the X chromosome, and it happens to be dominant. So equal male and females receive this trait. So then there's just some practice. So at this point, if you want to bow out, and if you think you got it and you want to just review and look over the notes, then you are welcome to do so. I won't hold you. Now, the rest would be just like if you were given a pedigree, if you're told what the disease is, you could know the inheritance pattern just by having that memorized. But you also should be able to practice by thinking, what were the clues I should be looking for? So what mode of inheritance is cystic fibrosis? I taught that one to you. You should just have it memorized, but also we can just look for clues. Not a lot of people have it in the pedigree, so it's more likely to be recessive. Male and female both have it equally, so more likely to be autosomal rather than sex-linked. So it's probably autosomal recessive. And then you could test it out by plugging in your genotype assignments. So if you think it's autosomal recessive, see if it works. Give everybody with the colored in shapes two recessive alleles, lowercase letters, and then work up from there and down from there and see where those alleles could have come from and determine, is it a possibility, okay? So in this case, it is autosomal recessive. If you just have it memorized, you'll know that, plus if you follow it through, it should work. So anyone with the trait has two lowercase alleles. How is that possible? Well, each of these parents must have also had one lowercase allele each, but they also had an uppercase dominant allele that keeps them from having the disease. And so that's why they're not colored. So all the parents of these affected kids have the heterozygous genotype. Okay, so this is just a reminder of some hints of what to look for, like starting points. If you're given a pedigree and you have to figure out what the inheritance pattern is, you can use these starting points. If you think it might be recessive, you'll look for anyone who's affected, but their parents are not. That's a big clue. Parent not affected, but kids are, then it's got to be recessive. If it's dominant, you'll likely see that the kids affected have a parent also affected. Then when it's X-linked recessive, you're going to see more males being affected, and you're going to see that they're getting it from their mother, who are carriers. If it's X-linked dominant, you're more likely to see, even in the sexes, male and female, and you're going to see that females are getting it from either parent, or the males might have to have a mother who's affected, because for a male to get an X, he gets it from his mother. Okay. So those are just some clues to look for. Remember, not rules, they're clues, hints. This is just a summary reminder of which diseases we've talked about or you've seen in the notes in the past fall into which categories of inheritance. This is definitely something that you should try to study and commit to memory so you know some examples of diseases that meet each inheritance pattern. And then I just have some more practice. So again, you would look at the pedigree and you would ask yourself, is it appearing frequently? Is it skipping generations? So is there someone who has it but their parents don't? And then you use those clues to tell you, okay, I think it must be recessive because it doesn't happen frequently and these kids have parents without the disease. So I think that the kid has the 2 recessive alleles and the parents must have one of each. They must be heterozygous. And that's how we can show that this is possibly going to work for recessive autosomal inheritance. I used E for earlobe because I mentioned it's earlobes. And then it does work if you follow it through. Okay. One more practice. This one's tongue rolling. If you see it happening throughout multiple generations, it's more likely that it's dominant. If every kid affected also has a parent affected, then it's more likely that it's dominant. And you could start plugging it in and just try it. So anyone who doesn't have the colored in shape must be recessive. And everyone who has a colored in shape has to have one dominant allele. Remember, dominant shows up with only one copy. They can still be heterozygous and have one capital and one lowercase and show the trait if it's a dominant trait. So you're going to work your way through everybody who's not affected, give them the recessive lowercase letters, and then work your way from there to figure out who has heterozygous genotypes of the dominant trait. Okay, and that one person you can't determine if they have 2 uppercase or not. This one's talking about color blindness and flat out tells you it's sex linked. So then you're going to remember to use your sex linked genotypes. So 2 X's for females, X and Y for males. So that's where you're going to start. You're going to see more males are affected than females. And for this female to be affected down here, if it's sex linked, she has to get it from both parents. So that means her dad has to have it, which he does, and her mom would have to be a carrier. So this is only possible for this daughter to get this sex-linked trait, colorblindness, if her mom is also a carrier for it. So the dad has it, he gives one allele to his daughter, and the mom must be a carrier. She gives the other allele to the daughter, and the mom also gives it to the son, but he only needs one, that he's getting it from the mom, okay? So you sign your genotypes. Here, instead of marking the X with an apostrophe, I just gave it a lowercase letter N. I don't know where N came from. But this mother here is the person you have to realize is a carrier, and that is the reason that this daughter was able to inherit 2 recessive forms of the X and therefore express this colorblindness recessive sex-linked trait. So you can plug in the rest of the genotypes. That's it for what I wanted to present to you. If you have any questions, I'd be happy to answer them. If you already did the Amoeba Sisters pedigree assignment and you have a question on that, you can certainly ask me about that. I don't have a copy in front of me, but I could probably dig around and find it online somewhere on the computer. And you're just gonna get more practice and more tries, and we'll see how it goes.
I just had to Zoom with Ms. Scherer, so I go, hi, Ms. Scherer.
Okay, no problem.
Hey, I have a question.
Yeah. Hi. What's up, Gabby? That's you talking, right?
Yeah, sorry, that was my brother. He asked me a question.
Okay.
I'm confused on the assignment with, like, the M&Ms or, like, the Skittles.
Okay, so if you want to discuss that, I am going to just stop the recording so whoever watches it later doesn't need to go through all of that. Let me see more. Okay, thanks for listening.